DKW Physics, I'm Mr. McConnelly, and today we're going to talk about radioactivity. Now, in most general sense, radioactivity is a spontaneous disintegration of the nucleus of an atom. And with that comes emissions of particles and radiant energy. Now, the way to just think about what's going on here. Basically, you have an atom that is pretty large. It's become pretty large. It's got lots of protons, lots of neutrons. And remember, keep in mind, that protons, if you had just a group of protons, they would not like each other because they're all the same charge. They would want to come apart, push apart from each other, repel from each other. And so the neutrons are like the buffer. They're trying to keep everything at a safe distance from each other. But when you get into these large atoms like uranium, plutonium, all of a sudden now there's just so much going on that's so large, eventually it becomes unstable. It becomes where it can't sustain for very long. And then you get these spontaneous disintegrations where you take uranium, pieces start being tossed off, and when those pieces get tossed off, you drop down to a different element. This is kind of a review of chemistry. If you are paying attention to chemistry, it should make a lot of sense. Well, we're going to talk about it from a physics perspective now. And the first person we need to talk about is Henry Becquerel. I'm not sure that's really the way you say his name, but that's the way I'll say it. And he actually was the one who discovered natural radioactivity in 1896. Now, I had some students look up Ernest Rutherford, the next person, and basically somewhere around 1900, give or take a year or two, right after Henry had come up with this idea of radioactivity, Rutherford comes up with two very important experiments. And these experiments help us to understand what's happening with radioactivity. The first one, which is going to involve the third left-hand rule also, plays out like this. He takes a chunk of lead, and he drills a hole into it, and then he puts a blob of radioactive pitch. I don't really even totally understand what that means, but it was some radioactive mess that he had come up with. And so lead, he had already figured out, was a good shield of radioactivity. And so by drilling the hole, it only allows the radioactivity to escape the lead block in one direction. It's going to come out this way. And that way, he can kind of focus his attention at one spot instead of the radioactivity going all directions. He might miss something. He can kind of focus his attention. Well, he comes up with this great idea. Basically, it was like a piece of film. Now, old cameras, back before your time, or when you were little kids, these cameras used to use film instead of a digital method, and the film would be exposed. And what that meant is when the light hit the film, it would change it from a dark black to a lighter color, and depending on how much, it would change it more or less, and you would actually create an image that way. Well, so they had already invented films of different sorts, and so he was going to use that because he figured, well, if there's radioactivity coming out of here, it should actually expose or turn the film a lighter color, and I'll be able to see that it came out. And he expected to see a blob right about here where the film was exposed. That's not what he got. What he actually got was an exposed spot here, an exposed spot here, and an exposed spot here. Oh, and I forgot to mention one thing. The first time he did the experiment, he did get one blob. Then, he put a magnetic field here. Then he got 3 blobs. Bam. Now I'll tell the story right. So he gets 3 blobs after he puts the magnetic field there. And let me kind of take you through how that works. So if you can think of the magnetic field as into the board. And so then with your third left-hand rule, your fingers will be pointing into the board. And you think of this right here as being a tiny little negative. Let's assume there's a negative in this radioactive emission. So that would be your thumb. So you got your fingers into the board and your thumb is pointing that way to the right of your left hand. That means, according to the third left-hand rule, the force is going to be down. So if there was a negative, it would get curved down. So this must be something negative. If there was no charge, the magnetism wouldn't affect it anyway. So what would happen? Straight, no charge. And if it had a positive charge, it would be pushed opposite the way the negative was pushed. And so, Rutherford was kind of piecing this together in his mind, and he's like, wow, there must be a positive, a negative, and a no charge that is given off by radioactive decay. And so he was a very imaginative guy. And you know what he named them? Alpha, beta, and gamma. Which in the Greek alphabet is A, B, and C. He wasn't very imaginative, okay? So A, B, and C he called them. And the symbols go like this. An alpha is a fish swimming to the left, the gamma is a fish swimming down, the beta is usually denoted like that. Now this was huge news. Huge news, and it took people a long time to kind of accept this. But eventually they realized, yeah, he's right. He's separating, and there are 3 different radioactive emissions that are given off. And then that opened up a whole field of study where people started diving in and trying to figure out, what is this really? What are the characteristics? And what's this? And what's this? And they have spent years and years after 1900 trying to figure out all the details. So that's one of his experiments. The other one was a popular one called the gold foil experiment. And with the gold foil experiment, he basically just had a piece of foil that was, like you think of aluminum foil, tin foil, and except gold. And then, same way, he's going to shoot radioactive emissions at the gold foil. And then behind here, so he can see what happens, what gets through, he again puts a piece of film. And what do you think happens? Some of you remember chemistry? Most of it goes straight through. Most of it continues on and the film gets exposed. And what does he conclude by this? Well, he concludes, first of all, a real important one, is that most of the atom is empty space. Okay? Most of the atom is empty space. Like, the chances are, if you send something towards it, it's just going to short it through because it's just not much there. I mean, foil looks like a solid, but when you really zoom in on it, this is what he was envisioning in his mind, when you really zoom in on it, it's just got tons of holes in it. Things like really easily porous, and the radioactivity can zip right through it. So that was the first thing. He also realized that most of the mass of an atom is concentrated at the center. Which eventually leads into the idea that the center is what we'll call the nucleus. Okay? Because the nucleus is the density packed, the most mass is in the middle, and then there's mass around it, but he didn't really understand what was going on yet, because we're still really early on in this whole discovery process. And finally, that the overall mass was too large to be just protons. Which leads him to what? Realization. There's neutrons there. Okay, so eventually this helps him realize neutrons, this helps him realize nucleus, this helps him realize the layout is very hollow of an atom, kind of pass things right through it. So for today, this has been our historical perspective of radioactivity.